The key feature of ORM is the mapping it uses to bind an object to its data in the database. Mapping expresses how an object and its properties and behaviors are related to one or more tables and their fields in the database. An ORM uses this mapping information to manage the process of converting data between its database and object forms and generating the SQL for a relational database to insert, update, and delete data in response to changes that the application makes to those data objects. An ORM performs the rather amazing task of managing the application's interactions with the database. Once you've used an ORM's tools to create mappings and objects for use in an application, those objects completely manage the application's data access needs. You won't have to write any other low-level data access code. But strictly speaking, you could still write that kind of low-level code to supplement the ORM data objects, but this adds a significant layer of complexity to an application that, I have to tell you, I've rarely found necessary when using a robust ORM tool. It really is better to stick to one or the other technique and keep the application simpler and more maintainable. There are a number of benefits to using an ORM for development of data-based applications. The first big one is productivity. The data access code is usually a significant portion of a typical application, and the time needed to write that code can be a significant portion of the overall development schedule. When using an ORM tool, the amount of code is unlikely to be reduced. In fact, it might even go up. But the ORM tool generates 100% of the data access code automatically based on the data model that you define in just mere moments. Now you're likely to have to supplement that code, but at least you're starting with a solid code base that performs all of the standard kind of operations that you're likely to need to do with data. Another benefit is in application design. A good ORM tool designed by very experienced software architects will implement effective design patterns that almost force you to use good programming practices within an application. This can help support a clean separation of concerns and independent development that allows parallel, simultaneous development of application layers. Another benefit is code reuse. If you create a class library to generate a separate DLL for the ORM-generated data access code, you can easily reuse the data objects in a variety of applications. Just add a reference to the DLL and you're good to go. This way, each of the applications that use the class library need to have no other data access code at all. Really nice big benefit. And then the last big benefit is application maintainability. All of the code generated by the ORM is presumably well tested. So you don't need to worry about testing it extensively within your application. Now obviously you need to make sure that the code does what you need, but a widely used ORM is likely to have code banged on by many developers at all skill levels. Over the long term, you can refactor the database schema or the model definitions without affecting how the application uses the data objects. All right, now the flip side is that there is one potential downside to using an ORM, and that's performance. It's very likely that the data access code that's generated by the ORM is more complex than you'd typically write for an application. This is because most ORMs are designed to handle a wide variety of data use scenarios. Far more than a single targeted application is ever likely to need to use. Complex code generally means slower performance. But a well-designed ORM is likely to generate well-tuned code that minimizes the performance impact. Besides, in all but the most data-intensive applications, the time spent interacting with the database is a relatively small portion of the time the user spends using the application itself. Nevertheless, I've never found a case where the small performance hit wasn't worth the other benefits of using an ORM. But you should certainly test it for your data and your applications to make sure that the performance is acceptable. Now, there are a number of ORM tools available for .NET applications. You can look up a Wikipedia topic called List of Object Relational Mapping Software. So that's a pretty extensive topic that has a lot of different tools available. It's actually pretty surprising the number of tools available. Now, that page is for all software platforms, but there's a number of .NET ORMs there. Before Microsoft introduced Entity Framework, the open source NHibernate was probably the most dominant ORM tool. NHibernate is ported from Hibernate, which is a Java ORM tool that has been available for years. But because Microsoft now bundles Entity Framework with the .NET Framework and incorporates extensive support for it in Visual Studio, Entity Framework has become the dominant ORM in the Microsoft development world. ADO.NET has long provided a variety of generic data objects that you can use to access data in a variety of data stores. A few of the most common objects that you probably have used since the initial debut of the .NET Framework in the early part of the millennium were things like SQL connection and OLEDB connection. And these represent a connection to a SQL Server database and an OLEDB database, respectively. So you would create the object, set some properties, and it would go out and connect to a data store. Another couple of common objects are the SQL data adapter and the OLEDB adapter. And these represent data commands and a database connection used to read and update a database. So a data adapter uses a connection object, SQL connection or OLEDB connection object. And then there's the dataset and data table. These are in-memory data caches. And a dataset has one or more data tables, and the data tables are used to access and update data as a generic data container with various data-related behaviors. And then there's the SQL data reader and the OLEDB data reader. These provide a forward-only stream of data from a SQL server or an OLEDB database. These objects don't actually contain data, as you probably have the concept of an object in memory. But what they do is provide a fast way to retrieve data for immediate processing or caching in other objects in memory. Together, all of these objects provide a means for accessing data in a data store, manipulate it, and persist updates back to the data store. The two data containers, dataset and data table, can contain any two-dimensional data, rows and columns, that you read from a data store or generate in memory as the application executes. They contain properties and behaviors that let you perform tasks, things like getting a list of the fields for a data table, whether it's a standalone object or part of a data set, read each row of data as a whole or field by field, compare updated field values in a row to the original values that are read from the data store, or track changes in values in new and deleted rows, and save changes back to the database. A lot of things that these objects can do. The objects really are remarkably versatile, and developers built untold numbers of applications using those objects. But, and you probably guessed there was a but coming, right? As useful as these objects are, there are a number of problems that developers had to overcome, making data code unnecessarily complex. And a few of these included things like strong coupling between an application and a database. The application code that reads data using a data adapter or a data reader needs to know the structure of the data coming from the database in response to some kind of query. This means that any change to the database schema requires a change to your application code. And the problem is magnified with the more applications that use that database. There are some ways to mitigate this issue, but that means more complex code. Another problem is loose typing. Datasets and data tables primarily rely on strings to identify the table or the record set and field that you want to access or update. The objects have to be able to handle any kind of data contained within a field, string, dates, numbers of various kinds, and so on, and therefore return generic objects of type system.object. You often have to perform an expensive conversion to a specific strong data type before using it, another way that the application is strongly coupled to the database. Now, data readers have type-specific methods to retrieve specific data types from a field, which causes strong coupling because the code needs to know the data type of each field. And then another problem is object interactions. A data set is able to contain relationships that define how the data in various data tables are related to each other, something like what foreign keys accomplish in a relational database. But extracting related data requires some often complex, unintuitive code, and sorting and filtering can be a challenge as well. All right, so you can start to see that there's various problems with using the generic ADO.NET objects for data access, even though developers have used these objects for years. The problem is that every one of those non-trivial applications has had to deal with the object's limitations over and over and over again. But for about a decade, it was the best we had, short of manually developing custom entity objects that encapsulate all the data access code, but require massive amounts of custom code. But entity objects are a big improvement over generic data objects. Instead of instantiating a dataset object that contains data tables for customers' orders and orders details, you can instantiate a customer's object with custom properties related to being a customer, and order details, along with navigation properties that easily access related entities and the behaviors that are germane to those entity types. An application can then make use of these entity objects in a very object-oriented fashion, making it a lot easier to work with the underlying data that is all nicely encapsulated in a customer object, for example, that it acts like a native customer object should. The interface of an entity object can closely mirror the tables and fields in a relational database, such as with an entity object for each relevant table and properties for all or most fields in the underlying table. Or the object can be completely different, with maybe a single entity object that uses data from multiple tables in the database, with properties that bear no resemblance to the fields in the various underlying tables. Or, probably really more likely, something between those two extremes, whatever makes the entity objects most useful for applications that use them. No matter how you design the objects, somewhere deep within them, objects have to have a mechanism for mapping the database schema to the properties of the entity objects. And as you'll see a little bit later and throughout the course, Entity Framework has all the features it needs to manage this kind of mapping for you. All right, so there's a lot of benefits for using entity objects instead of the generic data objects. The first is strong typing. Each property of an entity object can be a specific type needed for the data exposes. Strings can be strings, dates can be dates, numbers can be whichever of any of several types to most closely match the data, and so on. You no longer have to do any type conversions when using data in an application. The entity object takes care of that when reading and writing the data from and to the database. Now, related to strong typing is compile time checking. The generic data objects mostly return data as objects, so your application code has to manage conversion and you have to make sure it's right. With entity objects, the compiler can take care of this task for you, dramatically reducing the potential for runtime bugs. Now you can design these entity objects to encapsulate the persistent data store so that the application doesn't need to know anything at all about how and where the data is stored, or even its structure. This is known as persistence ignorance, in which information about persistence is segregated or separated from the business logic. It disconnects the data storage from the application, making both resilient to changes in the other, and really is a major benefit for using entity objects. Another benefit of entity objects is productivity. Productivity again. This is a benefit of both strong typing and compile type checking, as well as the inherent design of entity objects. And the thing here is that application code is far easier and far faster to write. You don't have to worry about writing and rewriting code to connect to the database or to manage the flow of data between objects and the database, as you do with the generic data objects. Even better, IntelliSense and Visual Studio can help you in writing clean, correct code, taking advantage of the implementation of business objects. The bottom line is that entity data objects provide a far richer way to access data and manage its flow between the application and the database than the generic ADO.NET objects. You can do a better job of modeling the real world with entity objects, and they can have behaviors that automatically know how to perform various actions. Now, when you decide to make the switch away from writing custom data access code and start using an ORM like Entity Framework, you'll have to change how you think about using data within an application. This is because you're no longer interacting directly with the database from within the data layer of the application. Instead, you're working with generated objects based on the data model that you design using the ORM tool. The two paradigms are quite different, but the good news is that you'll be working with the same kind of objects that you use extensively in any .NET application. Just keep in mind that the model is not the database, and you'll make the mental switch far more easily. When using the classic ADO.NET data objects, data sets, data tables, data readers, and so on, you have to write a lot of code to get data from the database. You have to set up the connection, instantiate the various objects, provide SQL statements or stored procedure names, execute the queries, and process the data, often by extracting pieces of data from the results and populating the properties of business objects with it. You use the data objects to query the database directly, which couples the application closely to the database schema. But when you work against the entity data model and objects, you're essentially querying a schema that reflects the application's business model. You don't have to do the work of sorting out all the data from the query results and get it into the right properties in the right objects. The objects themselves take care of all that. The objects keep track of data that the application updates, inserts, or deletes, and takes care of updating the database with just those changes without needing to send the whole load of data back to the database.